Hey everyone, this is Gavin Adams, Solutions Architect with AWS.
Hi, this is Richard Kang, Solution Architect from AWS as well.
Great, so let's go ahead and get started. So today's agenda will be covering a few different things. We're going to first start off and just do an overview of what are solution accelerators and why would you want to use them. We're then going to go through a couple service overviews, Greengrass and IoT Core, because these are intrinsic for how the accelerators work and also how IoT workloads are comprised and built. Then we're going to do essentially a tour of the accelerators themselves, what we have out there and different use cases for them. Then we're going to transition into a demo. We're going to deploy one of these accelerators from start to finish so that you can see the operations for deploying this in a prescriptive and consistent manner, seeing it in operation, and then also being able to tear down or destroy the demonstration once done. And then finally, we'll open it for Q&A, and hopefully we'll have some good feedback there. All right, so let's go ahead and start off with what are solution accelerators? Normally, customers will come to us and they'll have an idea. For instance, it may be an oil and gas customer that has got a large industrial plant where personal safety or worker safety is important. And they also have cameras out there, and they say, if I can take video of where all my workers are, in the event of an emergency, I'll know exactly how many workers I have in different locations, and I can make alerts to ensure that everybody is in a safe area. So they take this idea, and they come up essentially with an architecture. They know they're going to be using machine learning. They're going to be using computer vision at the edge. They want to be able to process and transform this data. They want to do inference on this, and then be able to, in the event of an emergency or an event, alert people to actually take precautions or to go into safe areas. So they have the idea. They know how to do a lot of the cloud-based components. But when you try to merge the two together, is that, especially when you're using edge computing such as Greengrass, it becomes problematic for how do you actually build some of these edge solutions. Very versed in the cloud, but not understanding some of the Greengrass components itself. So what we've come up with is a series of Greengrass accelerators or edge compute accelerators, which cover common patterns using Greengrass, and then having reference architectures or reference patterns for actually how to deploy those. So for instance, in the case of doing that computer vision or machine learning at the edge, we have a machine learning inference accelerator. Imagine another customer comes and they have an autonomous vehicle where they want to collect a lot of data locally in a car, do transformation of that data, maybe from different formats such as CAN bus or something that's very specific to that vendor, and then be able to send that up into the cloud. So we have another accelerator which covers extract, transform, and load, and showing how that can be done locally using Greengrass and other services on the actual Greengrass core itself. Another pattern, maybe that you want to take data in from a disparate or a lot of different sensors or devices inside of a factory. You want to then stream that data to local displays or do processing on that in a streaming type of format, both locally and sending it to the cloud. So in this case, you may actually use the Stream Manager Greengrass Accelerator, which shows how to do this end-to-end. A couple things here is that the accelerators cover common use patterns, but they're not prescriptive in exactly how this takes place. Every customer is going to have a different approach for how they want to do the actual operations at the edge, and we're showing you essentially one way that this can be done, and then how you can modify or take the examples in the code that we've provided to modify or augment this for your actual use case. So we talked a lot about Greengrass, and having familiarity with that will be important. So let's just do a quick overview of some of the services and capabilities of AWS IoT Greengrass. To put it simply, Greengrass is how do I take cloud capabilities and apply them to the edge? And AWS IoT Greengrass is the service and the software that allows you to do this, to extend cloud capabilities to an edge device that you own with software that AWS provides. And essentially, it addresses three different components. One is that transmission of data back to the cloud from the edge has latency involved. And if we can do operations locally, so this may be that you are looking for alerts and you want to take action on them in microseconds or milliseconds, we can all do that locally without having to send that to the cloud, have the process take place, and then have the response come back. Another case is that Greengrass is normally deployed in environments where there may or may not be good internet connectivity or network connectivity, or that you're running on mobile networks where it's very expensive to transfer data to the cloud. So in the case of machine learning, where you're doing computer vision and you've got megabytes of data per image, is that being able to process that or act on that locally is much better than having to send it to the cloud. And then jurisdictionally, if you're in environments where data simply cannot leave an environment, imagine a hospital or medical facility where it's mandated patient data must stay locally, is that Greengrass allows you to still do those cloud capabilities locally without ever sending the data outside of that particular facility. So the three main use cases, these differ from the accelerators, but they kind of align to them, are what we show here. Local actions, the ability to have a closed loop operation locally, where somebody can press a button on a connected device. Greengrass locally can infer what should be taking place, and then Greengrass can say, oh, I need to stop a piece of machinery, or I need to stop a process line. Machine learning inference also is very important. By being able to train a model and deploy it to the edge, machine learning allows you to do the inference locally without having to send the data that you want to do inference on back to the cloud. So it's a very fast round trip type of operation. And then the extract, aggregate or transform and load just works with data in general. You can take a large amounts of data, do the transformations locally, throw away data that's not important, cleanse it, etc., before sending only the important data back to the cloud on those expensive and potentially high latency links. And we've got customers that are using Greengrass today in all these different environments. This may be where we've got customers on the smart factory or smart transportation who are doing this in industrial settings. We've also got customers, such as Centrica Hive and CradleWise, that are doing connected home environments. Again, Greengrass is being deployed into the home or into the factory, and then operating in that type of manner. A couple technical things just to go through. Greengrass has got some enhanced capabilities above some of the fundamentals we'll talk about. And this is where it takes a lot of the base components, such as machine learning inference, and helps automate that process. It allows you to basically train a model in the cloud, put it into a location where Greengrass can grab it, and then through a quick definition, this can be deployed to Greengrass where the machine learning inference component can reach out, grab that model, start running it locally, and basically have the inference operational. A couple other ones to call out is container support. Is that Greengrass does allow for running compute at the edge, and this is normally through Lambda functions. But we also have the capability of managing and orchestrating Docker containers also. So you can have a combination of Lambda functions or Docker containers, or a combination of both running on your Greengrass core. And then also the stream manager allows you to have a standardized way to collect data, create local streams where you can then have producers placing data onto the stream, and then local consumers, which can be either Lambda functions or even other processes on the Greengrass core device itself to actually consume and operate on those pieces of data. Foundationally, Greengrass has got a lot of components, and the ones that are specific and customers use a lot are local messaging triggering. A local message broker that allows Greengrass aware devices to connect locally, and using the MQTT protocol, transfer or publish and subscribe messages back and forth, either from device to device or from device to local Lambda functions and vice versa. Again, we have that ability to deploy Lambda functions. So you basically write or build these in the cloud, package them up, and they are delivered and executed locally in Greengrass. And these can either be Lambda functions that are invoked or ones that are long-running processes. So essentially ones that are pinned Lambdas, if you will. The security model is also extended from the cloud down to Greengrass, so that Greengrass itself We'll still ensure that there's mutual authentication, so the high bar for security for connected devices and authorization, but it can also extend or vend out credentials to other Lambda functions to interoperate with other AWS services in a controlled manner. And then also, if you do have local resources on that Greengrass device, this might be a GPU or something that is a serial connection, Greengrass can provide those local resources to local Lambda functions to actually interoperate with. And there's the one kind of final slide for Greengrass is that it runs on top of hardware. So at the bottom of the slide is that we can run on either x86 or ARM-based architectures. Greengrass runs on top of the Linux operating system. So this can be your typical type of Ubuntu or SUSE type of distributions. But Greengrass can also run on top of OpenWRT or in the Raspberry Pi environment on top of the Raspbian operating system. And then Greengrass runs as software. It's a process and a set of services that run on Linux. And this can either be natively directly on the Linux operating system itself, or Greengrass can run as a container type of environment. And then when Greengrass is actually operating, it will do all of the orchestration for launching Lambda functions and Docker containers to interoperate when things are operational. And with that, I'll go ahead and turn it over to my colleague, Richard, to start talking about AWS IoT Core.
Thanks, Gavin. So as Gavin mentioned, from a device to the cloud, Gavin gave us a very good overview on the device side. Now, let's shift our gear to look at the cloud side, which is the AWS IoT Core. So the question is, if you can connect devices to the cloud securely and easily by knowing the states of everything, and if you are able to handle the data by making sense of the states, what problem are you going to solve? The reason we're asking that because we will do the heavy lifting of connections and the processing in the cloud so that you can focus on your business problem. Now let's look at the capabilities of what AWS IoT can offer. AWS IoT Core is a managed service. What does that mean? It means that we can scale based on your load and you pay for what you are using. And the keyword here is easily and securely, which I'm going to talk about why so when we do a deep dive on the components. But for now, let's focus on the capabilities of what AWS IoT can offer to your IoT applications. First, we need to make sure that all the devices in the field can be securely connected to the cloud. Once the connection is established, you want to be able to route the messages between devices and devices, or from devices to the AWS services in the cloud. Now, IoT devices tends to have the online-offline capabilities. So you want to be able to interact on knowing the last known state of a devices, even though it goes offline. So we have these shadow capabilities in the AWS IoT Core. And lastly, once you have the data sent to the cloud, you want to make use of the services we offer in the AWS Cloud. For example, the analytics or SageMaker for the machine learning training, as what Gavin mentioned just now. With these capabilities, let's look at the components that AWS IoT Core offers. Now, the first capabilities is the identity service. What does it offer? It allows you to identify each of the devices out in the field by using X509 certificates. Once a device on board and registered with the AWS IoT Core, then you can attach a fine-grained policy to restrict what the device can do. For example, what the topic it can subscribe to, or what the topic it can publish. Because on the field, we have a variety of devices. You want to have that fine-grained control on how devices can communicate with each other. The next service is the device gateway. Device gateway is a long-lived bidirectional communication channel that runs over TCP and over a TLS 1.2. Devices also can do custom authentications with the device gateway. Third component is a message broker. A message broker is a scalable, low latency, and reliable MQTT protocol message broker. So as I mentioned, your devices might want to communicate with each other. So devices can publish and subscribe to and from other devices or AWS services or other applications. Now, the important concept here is we decoupled the publisher and subscriber. Because, as I mentioned, the devices might potentially go offline, right? So if you have a device-to-device communications, we want to make sure the publishers is loosely coupled from the subscriber, even though when the subscriber or the devices might be offline. So leveraging the message broker allows you to do the loosely coupled architecture. The message broker runs on the MQTT 3.1.1 specifications, which allows you to customize a topic structure, such as you can subscribe to a wildcard or a hash. Next, we'll talk about the rules engine. A rules engine takes a message and route to other AWS services. It offers a SQL-like syntax, which allows you to select a specific information from the message payload or from the topic. And from there, you can specify the actions, such as you can store the message in the S3 or republish the message to another topic. Next, we have device shadow. If you recall in the previous slide, we talked about when the device is offline, you want to be able to know the last known state of a device. Device shadow allows you to have the capabilities. A device shadow is a virtual representation of your device in the cloud. It's a way of doing command and control. If your application specifies a specific setting of your device, the shadow will store and sends out a delta message to the cloud, to the devices, pardon me. And if the device is offline, the application can retrieve the last state of a device information from the shadow, either using API, which comes in a JSON format. Registry is an immutable data about a devices, such as a serial number, manufacturing date, manufacturing ID. The information that does not change after the device is provisioned. Now, it's very useful because when a device is in the field, you might want to do over-the-air update to some devices, maybe like devices that manufacture after a certain date. Now, you can use a fleet indexing, which will search the information in shadow and in registry. So once you submit the queries based on, say, the example of manufacturing date, then you can identify which are the devices that can push a certain update. And that's very powerful in the device operations perspective. All right, now with the Greengrass, as Gavin mentioned, the edge side, and the AWS IoT Core, the cloud side, let's look at the solution accelerators. The solution accelerators can be found in the IoT solutions repository. The URL is provided in this slide. The ETL, the extract, transform, load accelerators, and the machine learning inference accelerators is part of the solutions repository. The ETL accelerators helps you to accelerate if you have a solutions at the edge that you want to look at extracting the data ingestions and push it to the cloud. And the machine learning inference gives you some solutions. For example, you can bring your own model and upload the S3 bucket to the connectors. It helps you to accelerate if you have a machine learning inference at the edge requirements. Both web pages will point you to the same GitHub. And we have all these accelerators hosted in the GitHub so that we can encourage a collaboration. So if you have a use case that is pertaining to your organizations, feel free to fork these repositories and customize it. Or if you have certain changes, feel free to do a pull request. And we will look at it and how we can merge the solutions. With that, I'll pass it back to Gavin for the demo.
I'm using my local laptop for this demonstration. Everything will be done inside of the web browser, but we also have a local IDE just to show some of the files while the accelerator is actually getting deployed. So the first tab essentially will be for all the documentation, the repository, and then the deployment instructions. But then we're also going to be using a second tab, which will be logged into our AWS account with administrative privileges for deploying the accelerator. And then we'll use the local IDE with the cloned repository to take a look at some of the files while the accelerator is deployed. So the first thing that we'll do is go to the solution repository page and scroll down until we get to the section that has the accelerators. From here, we'll click on the Get Started Now link for one of the accelerators, which will take us to the detail page for that particular one. The Get Solution Accelerator link here, in turn, takes us to the GitHub repository for that particular accelerator. Since we want to work with the Stream Manager one, we'll click on the main AWS IoT Greengrass Accelerators link at the top, and then from there, scroll down to the list of accelerators and click on the one for Stream Manager. This link will take us to the Stream Manager's main README page, which describes the Stream Manager and typical use cases such as video processing or high-volume data collection. Then also has a diagram showing all the various components of the Stream Manager, how they interact with each other locally and also with the cloud itself. The diagram shows the components from both the Greengrass side on the left and the AWS Cloud side on the right. And then below, it shows more of the details for the various components, how the functions work, how the managed container works, etc. We start by generating sensor data simulated and push that to the stream producer function. The stream producer function then sends it to the local data stream, which is read by the stream aggregator, which does an aggregation and transformation of the data, and in turn sends it to the aggregate data stream. Those aggregate data values every 5 seconds are also read by the Docker container for the local display via the Flask application, which we'll show. The local data stream and the aggregate data stream are also configured to send their records up to different services. AWS IoT Analytics for the local data stream, and to Kinesis data streams for the aggregate data stream. Note that these are actually deployed as part of the accelerator, but we're not going to cover these in this particular demonstration. However, the documentation below will show how each of these applications is receiving data from its respective data stream. So if we take a look at some of the details here, is that the stream producer is going to be generating 20 readings per second, sending those to the aggregator, which in turn is going to average those on a 5-second interval. That's what the Flask application essentially is going to be reading and displaying inside of our web application itself. We have some more details in regards to the design pattern for how Greengrass running in a container itself can also manage other Docker containers via Docker Compose through the underlying Docker daemon running on the actual host. So this can be on a laptop or in our case via Cloud9. And as we scroll down, we can see what the folder structure of this portion of the repository is. Then more importantly, the steps on how to actually deploy the accelerator. This can be done either locally on your own laptop or via the Cloud9 IDE in the cloud. Both of those do have prerequisites that have to be met. But if you're doing this locally, there's the assumption that you have these components installed and can essentially walk through the steps. So we give you essentially the guidance for the main components of prerequisites, cloning, etc. For Cloud 9, we're a lot more prescriptive in what the steps are. So from this perspective, we're essentially going to launch a Cloud 9 environment, and then we're going to go through each of the steps to do the prerequisites and the deployment. This is actually going to generate the CloudFormation template and deploy it. A couple things: when you actually create your Cloud 9 IDE, ensure that you actually select Amazon Linux and a T3.small instance size. This is important, and that Ubuntu is not supported in this environment. So with Cloud 9 launch, we're going to have to do some prerequisites to essentially get the environment ready for running both CDK and for Docker itself. So we go to the console, we go to Cloud 9, and we'll open the Cloud 9 IDE that we've previously created. So this is the default that you're going to see. And just to make this a little bit easier, we're going to close a couple of the windows that are not necessary. So we'll close down the bottom one, we'll close down the Welcome tab here, and then using the little green plus symbol, we'll launch a new terminal. Once the terminal window is launched, we'll then go back to our documentation and copy the first set of steps, which are the prerequisites. So we'll simply select, copy all of these, go back over to Cloud 9, and paste these in. And what this is going to do is install the version of the CDK, the Cloud Development Kit, that is specifically made for this accelerator. And it will in turn then go and do some additional steps, such as bootstrapping CDK if it's not already done, installing Docker Compose locally so we can actually operate with it. And then the final step it's going to do is open up a couple ports so that we can get back to the Cloud 9 instance for that Flask application, which is going to show the web app for our Docker container that Greengrass is managing. The final step is we want to do a reboot at the very end. So we do a sudo reboot, hit return, and this will restart the Cloud 9 instance with those changes, which will allow for both Docker to run and Greengrass to run locally inside of Cloud 9 itself. The reboot of the Cloud 9 instance can take a couple minutes. So in the meantime, let's go back over to the IDE and take a look at some of the file structures for the accelerator. Inside the repository structure, we'll open up one of the accelerators. And you'll see under the extract, transform, and load, we've got a CFN directory, which is for CloudFormation components. This is what actually deploys to the cloud and uses the older mechanism of configuration files, such as YAML or JSON. If we open up the Stream Manager accelerator, we can see we have the CDK directory or Cloud Development Kit. And this uses TypeScript to declaratively generate all of our resources. So with that, we've got the Cloud 9 environment rebooted, and we can see we've got the little twirly for the terminal there. If you see that, feel free to go ahead and close out that terminal and just launch a new one. We don't need it. We've already done all the prerequisites. So use the same mechanism of the green plus sign and open up this window here. We'll go back over the documentation and move on to the next step, which is to build and deploy. It's broken down into 3 different sections, and we'll focus first on doing the actual cloud deployment component, or CDK. So we'll copy that set of lines there, which will clone the repository, install all the dependencies for Node.js, the NPM components, and then actually issue the CDK deploy command, which will go out and actually do the full deployment of all of our resources. So the NPM dependencies and the compilation takes us a few seconds. And then we get the final command there, CDK deploy. We hit return. And what this will actually go do is list all of the resources we want to have created and then ask for a confirmation. So we say yes, hit return. And at this point, the CDK command line will start to do the CloudFormation deployment. It does this through a couple different steps. First, it does a full compilation of our code, creates the actual CloudFormation templates, and then actually calls the CloudFormation service to instantiate or start this process up. It'll take a few minutes to actually go through and complete because we're deploying a whole bunch of IoT services, Kinesis data streams, analytics, supporting Lambda functions and such. So in the meantime, let's take a look at a couple of the different files for the Stream Manager while that operation takes place. So the first things we mentioned is that we've got the CDK directory, which describes how infrastructure is actually defined. So we'll open up the index.ts file, which is the main one. And what you see here is we've got the imports for a variety of different resources. These resources equate back into either common CDK type of assets, Greengrass, S3 Kinesis, or in certain instances where we needed to create our own custom resources or have constructs that had more details around this, such as IoT analytics. So it's all based on a top-level class, which is the Greengrass Stream Manager stack class. And here's an example of where we're creating an S3 bucket. Here's where we're creating some of our different services, such as the IoT analytics component, applying all of our channels, data, pipelines. And then we've also got all of the custom resources down below. Besides creation resources, we also generate outputs. For instance, we have the certificate, the private key, the thing name, etc. Then down below, we've got all of the Greengrass related components themselves. Let's take a look at one of the components or constructs that helps automate this process, the creation of a thing, certificate, and a policy. Normally these are separate steps, but by having one resource, we can go through, do all of the creations, and then return the values that can be used by the Greengrass Docker configuration file itself. So we'll close out the CDK directory and take a look at the gg_docker directory. This contains all of the standard Docker file, Docker Compose components for actually building the Greengrass image itself, mapping all of the volumes for the certificates and the configuration, also mapping additional directories for taking a look at log files and such. We also map any additional ports that we want available for the Greengrass container to the outside world, along with networking configurations. So we'll close this file out and go back over to the Cloud9 environment, where the cloud deployment, or CDK, is now completely deployed the CloudFormation stack. The stack returns some outputs, which will be used in one of the next steps for taking these and transforming these into resources that are used by the Greengrass core itself. So we get the source bucket, certificate, private key, data endpoints, etc. from this perspective. So let's go ahead and take a look at what CloudFormation has actually done. So from the console, we'll go to CloudFormation, see that we have our Stream Manager Accelerator stack deployed. We then take a look at the resources that were actually created. And then for each of the resources, we take a look at the event stream to see how they are actually created over the course of time. So for each one, we have a create in process followed by a create is completed. So the next step is we want to run a little glue code here, which is going to take some of those outputs, transform them into the files and configuration that's needed by Greengrass. Very quick process, completed. So with that in place, we can now go and start doing the Greengrass configuration. So this will actually change over to the Greengrass_Docker directory. We'll do a Docker Compose build, which will build our image based on the default AWS IoT Greengrass image, along with some other additional dependencies we need for having Docker inside of the Greengrass image itself, and then some final dependencies we have for Python. So this is actually building the image locally inside of Docker so it's available to Cloud9 to actually instantiate a container. So as you'll see, we got the standard steps of going through the yum install process. We do the installation of the Docker Compose. And then the final steps are to go through and install all of the Python packages that are used by the Lambda functions on the Greengrass core itself, which are all inside of this Docker container. Once all of these dependencies are built up, the image will be complete and ready for Docker Compose to actually start the container locally here. So we do a docker-compose up --d, and that runs it in daemon mode, so it's in the background. And Docker Compose will show that the command is completed. It actually has started the Greengrass container, and at this point, it will start to pull down resources from the cloud. As we can see here from a Docker PS command, we've got the one container running right now, which is the Greengrass Stream Manager Accelerator. So at this point in time, if we go back over to our console, and from a service perspective, go to AWS IoT Core, we'll see under Greengrass and under Greengrass Groups that there's the group that was created by CDK, and then from a deployment perspective, it's successfully completed. Prior to this, it would have actually shown in process, but once the Greengrass container is started up, it actually says, hey, here I am. They want to pull down the deployment, which includes all of our Lambda functions. It has all the configuration for our connectors, which include things such as the Docker application deployment, how we're going to manage the Flask application, and then subscriptions, how different Lambda functions can talk to each other, and then finally the Greengrass core itself, which is the thing. So at this point in time, we're pretty much operational. The accelerator is running locally. As you notice now, we actually have two containers that are running. Besides the initial Greengrass container itself, we also have the one managed by Greengrass, which is the Flask application. And we'll show this later from the web perspective of how this is reaching into Greengrass. So to show a couple more different things that we can do when the container is running locally is in this directory, we've got a log directory. And this is where all the Greengrass logs are actually stored. If we take a look at this log, we can see we've got a system and user subdirectory. If we try to take a look at the system directory, we'll get a permission denied. This is an artifact for how Docker runs locally and that everything is done by root. We use the sudo command to view the contents of the directory and the contents of the file itself. Do the same ls log/system command again, and we can see that there's other log files inside of there. To take a look at those, we'll actually change this from a directory to tail, which will just show in real time what the contents of the file is. And we'll take a look at the runtime.log file. This is like the main one that shows all of the interactions. And you can see this is updated in real time as our functions are actually doing operations in the background. Using the local log files is a good way to see the real-time operation of Greengrass and also of your individual Lambda functions. At this point, with the accelerator fully running, all of these operations are taking place. We're generating data, we're putting it into the stream, and we're also sending this up to the cloud. So besides that, the other thing that we actually want to take a look at is that Flask application and how it's actually reaching into one of the functions to grab those values. So to do this, we need to find out what the IP address is of our Cloud9 environment. And you can see from there the 18.236. So we'll actually copy this URL and open this into a new tab. So this is actually running in the Flask application on Cloud9, reading values from the Greengrass functions, Lambda functions itself, and updating every 5 seconds. And since we're generating just sort of random synthetic data, is we'll see that the values for the temperature on the left-hand side and the vibrations on the right-hand side basically changing over time. So next we'll take a look at CloudWatch logs and see the log files that are sent up to the cloud instead of just locally. In CloudWatch, we're logging the error and warning information for the various Greengrass functions. So we go to log groups, and you'll see that we've got Greengrass log files for both Greengrass system and for the actual Greengrass lambdas, which are the user applications. So if we go ahead and take a look at one of the log file entries, and let's go ahead and focus on the system runtime one, just like we did from the command line itself, and we open up that log stream, we'll see that all we have are some error and warning entries. We don't have all those info ones that we're seeing locally. So this gives you the ability to send only the ones of importance up to the cloud. And in this particular instance, these are just artifacts of when we first start up Greengrass and it's going through its configuration functions. So nothing to worry about here. Our Greengrass accelerator is running fine. If we go back to the container, we can see that as we let it run, it's continuing to update the data points over time, and it'll continue to do so as long as the Flask application is running. And you can continue to take a look at some of the other information, such as where are the log files at, then also how to go ahead and see what's happening with IoT analytics or Kinesis data streams and the local Flask application. So the main documentation will provide that to you. So we're pretty much done. We have our accelerator running. Now we actually want to stop it. So the first thing we're going to do is, from a Docker perspective, do a Docker compose down. And this stops the running containers, both the Greengrass container and the Flask application itself. This is the way to gracefully shut down all of the components, the Greengrass daemon itself, along with the containers. If you receive an error message about removing the network, this is a normally seen occurrence when you've got multiple containers using a common network that are being shut down at different times. Sometimes you'll get it, sometimes you won't. To clear this out, do another docker-compose down, which will then finalize the removal of the network. And then we can actually run a docker- or docker ps command to see that there are no running containers. So at this point, Greengrass is shut down. If we come back over to the container web app, we'll see that we're no longer doing any type of updates because there is no backing containers for either the Flask app or Greengrass itself. So with that step, we've done all the shutdown locally. We now want to destroy the CloudFormation stack and all of the cloud resources. So we're going to do this using the same CDK command, but instead of doing a deploy, we're going to do destroy. So we change over to the CDK directory. And then we issue the CDK destroy command, which will essentially do a CloudFormation delete process. We hit return. We then do a confirmation that we want to destroy the stack. And just like before, we're going to see commands coming through, but now instead of doing create in progress and create complete, we're going to see delete in progress and delete completes. And we can actually see that this is happening over in the CloudFormation console itself, delete in process. And then if we take a look at the actual resources themselves, we'll see that they're in the process of being deleted. The delete process for the accelerators is a lot faster than the setup, and will take approximately 1 to 2 minutes, depending on which region you're in and which resources you have deployed inside of an accelerator. We can verify that this is actually taking place by going over to IoT Core and noticing that we don't have any things, which would be the Greengrass core. And likewise, we go to Greengrass groups. That group we had before is now completely destroyed and gone. And while the rest of these resources are being deleted, such as the Kinesis stream, is we can also go through and make sure that we're doing all the final cleanup. So all of the analytics and Kinesis data stream components are there, are been deleted, but we can also go to CloudWatch and ensure that those actual log files have also been deleted so that you're not being charged. We go to CloudWatch, we go to the log groups, and then you can select any of the particular log groups, and then under Actions, do a delete log group, which will delete all the log entries for that. Go through all the remainder of these to clean these up, and you won't be charged for the actual storage of the log files inside of CloudWatch logs itself. We go back over to Cloud9 and notice that the stack is completely destroyed. At this point, all the resources that were created have now been deleted. So at this point, the only resource that we actually have out there is the one we're running, which is Cloud9. So if we go over to the Cloud9 console, we ensure that our IDE has been selected, click on delete, and then type in delete. This will then start the shutdown and the deletion of that resource also. And if you notice, we go back over that tab, is that we're now getting the environment error that you can't access the environment because it's being shut down. So at that point, we're done. So in the matter of 20 minutes, we've taken a look at how the stream manager is actually set up, the design patterns associated with it, some supporting documentation, along with the steps for actually doing the deployment via Cloud9, start to finish, looking at the actual operation of both log files and the Flask application, and then fully destroying the stack. And with that, we'll go back to the webinar presentation. Thank you for your time in this demo.
All right, thanks, Kevin. That was an awesome demo. So to recap, as you can see from the demo that Kevin showed you, using the solution accelerators helps you to create the cloud side of the Greengrass configurations, show you how to do the Dockers, connectors, and most importantly, the solution accelerators give you an idea of how to use the stream managers. And after that, you can have the ETL as well as machine learning inference. So in other words, the solution accelerators is a complete solution that can deploy a common design patterns. And we help you to focus on your problem by leveraging the design patterns for your edge to the cloud solutions. And again, like I mentioned, it's available hosted in the GitHub. Feel free to incorporate into your workload, do the fork or do the pull request based on the changes or you found any issue with the solutions. And please contribute via GitHub. Thank you for using solution accelerators, and thank you for attending this webinar. Thank you, and send us any questions you have.